Okay, guys. So it's 5 p.m. in Moscow. We
Начинаем.
have we have 35 people coming and people still coming. So David, shall we start?
Whenever you're ready.
Okay. So thank you for everyone who joined our seminar today. It's my great pleasure to present our speaker, Professor David Cruz-Uribe. And I don't see the title of the talk, but I think that he can explain. Let me see. The title would be Norm Inequalities for Linear and Multilinear Singular Integrals on Weighted and Variable Exponent Hardy Spaces. Okay, great. Thank you. Thank you, David, and please go ahead.
Thank you, Alexey, and thank you all for attending. I had hoped someday to actually come to Rostov to give a talk, but I guess this will be the next best thing. So let me begin. First, let me acknowledge that this is joint work with Cade Moen, also of the University of Alabama, and my former postdoc, Han Nguyen, who's currently back in Vietnam. So let me lay the groundwork by talking about the linear case first. I'm going to talk about the linear case, shift to multilinear operators, and then go back and talk about the linear case again. So to begin, this is a very standard, what we call a convolution type singular integral operator. So we have a singular kernel K, and I want you to notice that we're assuming more regularity than is usually necessary. So we're assuming that we have derivatives on the kernel K up to some order n plus 1. And throughout this talk, capital N will always denote the regularity of the kernel. And it will play a very, very important role in what we do. So we have a kernel which satisfies the K estimates, and then is also the operator is bounded on L2. And then there's a well-known theory for these. And I'm interested in the theory of these operators on Hardy spaces. So the definition I'm going to use is the classical one using the Stein grand maximal function. So for p less than or equal to 1, function or even a distribution is an HP. If you take the grand maximal function of f, and it lies in the associated Lebesgue space, LP, and here there's going to be another constant n0. That's a very large number which we fix, and then you never pay attention to again. Okay. What this number is this comes out of the classical theory. This is the number which is large enough that all of the different definitions of Hardy spaces coincide. The grand maximal function definition, square function definition, the area integral definition now all coincide. And so we just convolve against phi sub t, which is a Schwartz function with, this just says it has enough decay. So the famous theorem, Pfefferman and Stein, is that if t is a convolution type singular integral and you have enough regularity, and notice the regularity depends on the dimension n and the size of p, and the closer p gets to 0, that means the more regularity you need on the kernel, then your singular integral operator maps functions in little a in HP into HP. Okay? So a lot of what I'm going to be talking about is an attempt to generalize in different directions this classical result. The first area of generalization is we want to move away from convolution type singular integral operators. Most of the theory in Hardy spaces was devoted to convolution type operators. So the classical theory, or if you even look at Stein's big book, he only talks about convolution type singular integrals. Here, however, we'll look at the non-convolution type, and the basic definition is K has a certain decay off the diagonal and a certain Lipschitz type continuity condition, and again, must be bounded from L2 to L2. But in this case, you can also have Hardy space estimates. So the original version of this theorem is due to Alvarez and Millman in 1986. I list myself because I'm going to be stating this theorem in the version we proved, which is slightly different than, but essentially the same as what Alvarez and Millman proved. So what do we have to assume? We have to assume that the kernel K has regularity, a lot of regularity, in the second variable, y. And we have to assume that the operator T satisfies a vanishing moment condition, in the sense that if A is an atom, so supported on a ball or a cube with capital N+1 vanishing moments, then T applied to A has to have N vanishing moments. Okay? So you, in some sense, you lose 1 degree of regularity when you apply T. This looks like a very strong condition, but if T is a convolution type operator, this is actually necessary. So it's a natural condition to impose on these non-convolution type singular integrals. And then, excuse me, the condition is exactly the same as the Pfefferman-Stein. Excuse me, Alexey, I'm getting very bad. Okay, let's stop. I was getting bad feedback. So, sorry, this condition is exactly the same as in the Pfefferman-Stein condition. So, the closer P is to 0, the more regularity you need for T to be bounded from HP to HP. Okay. So, my postdoc, Han, had been working on multilinear theory with his advisor, Lucas Kravchenko. And so he posed the question, could we extend results like this to the bilinear singular integrals? Everything we do is actually true for multilinear operators, but it's easy to state and describe what's going on for the bilinear operators. So a bilinear operator acts on 2 functions, f1 and f2. So you have a kernel in 3 variables. Again, this should be thought of as a principal value integral. We have to assume a lot of regularity on the kernel. We assume derivatives in all 3 of the variables. And again, we'll use capital N to indicate how much regularity we need. And then we just need T bounded on one particular triple. And for example, you can take Q1 and Q2 to be 2, and then Q is equal to 1. That's sort of the classic way to phrase it. Okay. And then Grafakos and Colton back in 2001 proved the following generalization of the Pfefferman-Stein result. So T is a bilinear SIO. P1, and P2 are all less than 1 and satisfy this triple relation. And if N satisfies exactly the same condition as in the Pfefferman-Stein condition, but here now P is the target space, then T maps HP1 cross HP2 into LP. Notice that we don't map into HP anymore, we map into LP. Okay? So the problem that Han proposed to myself and Cade Moen was, could we generalize this result to 2 different kinds of function spaces? Could we generalize them to the weighted Hardy spaces of Stromberg and Perchinsky, or to the variable exponent Hardy spaces, which were introduced by myself and Daniel Wang, and also independently by Nakai and Solano. Okay. So a few definitions here. For the weighted space, a weight is always, again, just a non-negative locally integrable function. And if you're not familiar with weighted theory, power weights, x to some power a, is the classic example. Okay? And then we turn this into a normed space or a quasi-normed space if p is less than 1 by just replacing Lebesgue measure by w dx. Okay. The class of weights we're interested in are the Muchenhaupt AP weights, which for p between 1 and infinity, we say w is an AP. The following somewhat complicated expression is finite. So it says that the average of w, so this integral with a bar means divide through by the Lebesgue measure of q. So the average of w times roughly the average of 1 over w. So if p is equal to 2, this is exactly the average of 1 over w. Is always finite, and it's uniformly bounded over all cubes Q. There's a lot of ways to think about this condition, but I find the best way is this condition says that W behaves locally like a constant function uniformly at all scales. And when P is equal to 1, you get the natural limiting condition, which says that the average of W is bounded on a cube is bounded by the essential infimum of W on that same cube. We're going to need a few basic properties of these weights. These more or less follow from the definition. So if 1 is less than P is less than Q, the classes are nested. So A1 is always contained in AP, is always contained in AQ. And so because they're nested, we can define this quantity, RW, which is the infimum of all P's, so that W is in the class AP. Okay, so this is going to show up in the hypotheses of all of our theorems. It tells us in some sense how good the weight is. And so you should think of A1 weights as being very close to constant, and then AP for P very large are much worse behaved weights. And then just for brevity, we'll just denote the union of all of these classes by A infinity. Okay. A key tool in our work is the Hardy-Littlewood maximal operator, which we define as just the averages of F over cubes. So you fix a point X, you take any cube that contains X, take the average over that cube, and then take the supreme. Okay? And then the big theorem, which is what justifies looking at these weights, is this characterization, W is an AP if and only if the maximal operator is bounded on the weighted space, LPW. And again, we will need that. That's in the background. We'll follow the Stromberg and Torchinsky definition of weighted Hardy spaces. So we'll say that W is in A infinity and a function F is in the Hardy space HP of W. Again, if the grand maximal function of F is an LP of W. Big difference now is these spaces are not defined just for P less than 1, but they're defined for all P between 0 and infinity. The grand maximal function is bounded pointwise by the Hardy-Littlewood maximal operator. So if P is bigger than 1 and W is an AP, the weighted Hardy space and the weighted Lebesgue space are the same, with equivalence of norm. But we're going to be interested in two possibilities. Either P is less than 1, or P could be bigger than 1, but W is not in the space AP, in which case the Hardy space is different from the Lebesgue space. Okay. Now I want to define the variable exponent space. So let me just introduce some basic notation. We'll be working with the set P0. These are just all the measurable functions which map Rn into 0 infinity. Okay. Never 0, never infinite. And in fact, if we let P minus and P plus denote the essential infimum and supremum, we'll always assume that P minus is greater than 0. So it can never dip down and be equal to 0. And P plus is always less than infinity. P plus less than infinity is mostly for technical reasons. We can generally ignore that, but at the cost of more work. Now, theoretically, we could do this for any measurable function, but to do harmonic analysis on these spaces, it turns out you need to impose some kind of regularity. Sharp regularity conditions aren't known, but the following continuity conditions are close to optimal. Okay. So the first condition here is what we call local log holder continuity. So when x and y are very close, p of x minus p of y vary like 1 over the log of x minus y. And then we require a decay at infinity. So there has to be some constant p infinity such that p of x decays to p infinity. And again, the decay is like 1 over the log of the distance from the origin. Okay. Using these, we can define the variable Lebesgue spaces. So technically, if you ignore the infimum, a function f is in a variable Lebesgue space if f of x to the p of x is integrable. Okay, but how do you turn that definition into a norm? So we use the Luxembourg norm, and this expression, it turns out, does give you a norm. And if p punto, the exponent function, is constant, then it just becomes the classical Lebesgue space with equality of norms. That's a nice little exercise to prove that. Okay. And then, just like in the weighted case, if we assume that P satisfies the two log Holder continuity conditions, and P minus is strictly bigger than 1, then the maximal operator is bounded on LP punto. Okay. So these are the spaces we're going to be looking at, and we use them to define the variable Hardy space. And again, f is in HP punto if the grand maximal function of f is in LP punto. Okay. And again, n naught is just some large constant we picked and then forget. And again, because of the boundedness of the maximal operator, if P minus is bigger than 1 and P punto is log Holder continuous, then you have equality of HP punto and LP punto. What we're going to be looking at, though, are exponents where P minus is less than 1. The whole exponent could be less than 1, but we also want to consider the possibility that in some places the exponent is less than 1, so locally it behaves like a Hardy space. And in some places the exponent is bigger than 1, and there it behaves more like a Lebesgue space. So these spaces have a fundamental inhomogeneity in their construction. Okay. And again, I'm just going to assume these and forget these going forward. All right. Let me now state my two main theorems. Okay. So again, joint with Cave-Mohan and Han Nguyen, let T be a bilinear singular integral operator. We'll fix P, P1 and P2 anywhere between 0 and infinity, satisfying this relationship. We'll let W1 and W2 be any weights in A infinity, and we'll define a third weight W is just the geometric mean of W1 and W2. Then if we pick n large, I'll come back to this expression, for n large enough, if we have enough regularity, then T maps HP1 of W1 across HP2 of W2 into the Lebesgue space LP of W. Okay, so this mimics the Grafakos and Calton result because we map into LP and not into HP. The regularity condition looks different because if you remember the Grafakos and Calton condition only depended on n, it was basically n times 1 over P minus 1. Here we have to have a stronger condition, and we take a maximum, and it involves this quantity RW1 and this quantity RW2, and the relationship to P1 and P2. And the reason for this is you have to disassociate and treat it this way, is these two spaces, HP1 and HP2, can behave very differently. So for example, again, if P2 is bigger than 1 and W2 is an AP2, then this is really just a Lebesgue space. Whereas here you could have P1 very, very close to 0, W1 in a very bad AP class with P very, very large. And so this space is going to be much rougher than this space. So your regularity condition needs to take into account the behavior of the two different weights. A weakness of this condition is we do not recapture Grafakos and Calton if we let W1 and W2 be the identity. We get the same condition, but only under certain assumptions on P1 and P2. So this result may not be optimal. Okay. The bilinear result for the variable Hardy spaces is almost exactly the same. So we define our exponent functions P punto, P1 punto, P2 punto, again, to satisfy this triple. And then as long as we have enough regularity, HP1 punto cross HP2 punto is mapped into LP punto. Okay? And again, the regularity depends on the size of P1 and P2, or more precisely, how small they're allowed to get. So if there's a location in the space where P1 and or P2 is very, very close to 0, then locally it's a very bad Hardy space, and therefore you need more regularity globally. So I now want to talk about how you will prove these results. And the first result I want to prove is the variable exponent result, because that's very easy in the sense that it's an immediate consequence of the weighted theorem and bilinear extrapolation. So a very important tool that I will come back to repeatedly in this talk is Rubio-de Francia extrapolation and its generalizations. So this is a result due to myself and Virginia Nybo. And it basically says, even if we put much stronger conditions on the weights, W1 and W2 are in A1, and we have any operator which maps HP1 cross HP2 into LPW, then if we have exponent functions whose minima are just a little bit bigger than P1 and P2, then T maps variable Hardy spaces into the variable Lebesgue space. Okay. And so this is what my German friends started calling the miracle of extrapolation. Okay. As soon as you prove the weighted theorem, you can prove the corresponding theorem in these variable exponent spaces for free. Okay. And in fact, there's some deeper theory floating around where you can replace variable exponent spaces by other Banach function spaces, say in the scale of Musilak-Orlich spaces, as long as you can prove an extrapolation theorem, which is fairly straightforward. Okay, so in some sense, we're not done with the variable exponent theory. That is entirely free from extrapolation. So now I want to talk about the weighted theorem, and this is much more difficult. And so let me sketch the broadest outlines of the proof. It's not even the proof so much as the pieces that go into the proof. So first, we need a finite atomic decomposition. It's classical that a Hardy space has an atomic decomposition. Stromberg and Torchinsky proved such a decomposition in the weighted case. We need more. We need what's called the finite atomic decomposition, which is a dense subspace which is composed of some finite sums of atoms, and the coefficients of those atoms can be used to approximate the 1. Okay. Then the proof requires a local and global decomposition. So we'll be working with atoms. So each atom is supported on a cube or a ball. So then we'll decompose the argument to be worrying about, are we close to the support of the atom, or are we far away from the support of the atom? Okay. In the bilinear case, this is much more complicated, because think of it this way. You're going to have your operator T applied to two atoms, call them A1 and A2. The supports of A1 and A2 could be very close together, or they could be very far apart. They could be of similar sizes, or one could be much larger than the other. So then you have to argue, are you close to the supports of both? Are you far away from the supports of both? Are you close to the support of one and far away from the support of the other? And as you could imagine, in the multilinear case, the problem grows exponentially. So really, one of the main technical difficulties in the multilinear theory is how to do a local and global decomposition. When you do that, for the global piece, you use pointwise kernel estimates. And here's where you use your assumptions about decay. Then for both pieces, you need vector-valued inequalities. The application of vector-valued inequalities is classical, goes back to Pfefferman and Stein. We need to use a lot more. And to prove them, here's where Rubio-de Francia extrapolation again becomes a very important tool. Okay. So, as I said, many of these steps are highly technical. and in particular, the local and global decomposition of the proof is very technical and not worth trying to present in the talk. So instead, what I want to do is I want to go back to the linear case, because one of the consequences of our proof techniques is we were able to give new proofs of weighted norm inequalities in the linear case. So here's the main result. Due to myself, Cave, and Hahn, and separately to Hart and Oliveira. Theirs actually came out about a year before ours did. Our results are essentially the same, but they state their hypotheses in a very different form. So in particular, they don't state the regularity condition on T in terms of vanishing moments, but in some sense, they take the dual of this condition, which requires some operator theory to define. But again, if we assume that we have n+1 regularity on the second variable, the kernel, n vanishing moments when we apply T to an atom with n+1 vanishing moments, then if n is larger than this quantity, T maps HP of W to HP of W. So this is a very good generalization of the Pfefferman-Stein result. Okay. And notice again, regularity depends both on how close P is to 0 and how good an AP weight W is. Okay. So how are we going to prove this? So this proof has exactly the same steps as the multilinear case, but they're a little easier so you can see what's going on. So first, again, we need the finite atomic decomposition. So we need a dense set of F in our Hardy space such that we can do two things. We can write F as the sum finite linear combination of atoms. The atoms have to have n+1 vanishing moments. They're supported in these cubes Qi. And here's the key condition that comes out. The Hardy space norm of F is gotten by the the LPW norm of linear combinations of characteristic functions of the supports. Now, if you're used to the classical theory of Hardy spaces, this doesn't look the same, because in the classical case, what would you do? You would actually have, excuse me, just a little LP sum of the coefficients lambda I. Again, in the weighted space case, you have to worry about the inhomogeneity of the space. Okay? That W behaves differently in different places, and so the atoms somehow behave differently. And that's captured by this more complicated expression. Okay. And then here's why we want finite atomic decompositions, because if F is written in this form, then we can immediately pull T through the finite sum and apply it to each atom. I would note that if you go back to the original paper by Grafakos and Calton in the multilinear setting, they originally dealt with infinite sums of atoms, with the classical atomic decomposition, and they pulled T through without comment. Okay. Later, Grafakos realized that this was a problem. He and one of his students, or a postdoc, had to prove that this expression for infinite sums of atoms makes sense. And that's already difficult in the linear case. In the bilinear case, it requires additional and, we think, unnecessary assumptions of regularity on the kernel. So this has the advantage, if you can work with a finite atomic decomposition, this lets you avoid those problems. Also, again, we've picked n0 in the background so large that we can replace the Hardy space norm by one of the classical definitions, the maximal radial, or the radial maximal function, where phi is just some nice, very nice kernel. Okay. And so now let's talk about what the local and global decomposition does. So the first thing is we replace the Hardy space norm of T, F by the Lebesgue norm of M of phi applied to T applied to F. So M of phi is sublinear, T is linear, so we can pull these through onto F, written as the finite sum of atoms, and then split the sum into two pieces. The first we call the local piece. We just restrict to not the support. If AI is supported on QI. QI star is just some large blow up. 10 times n times the radius of Q. Okay. And then the global piece is everything else, everything that's very far away from the supported Q. So we have to estimate this Lebesgue space norm and this Lebesgue space norm separately. So let me look first at the global piece. The following lemma is known, but I've actually not been able to find it written down anywhere, so I call it folklore. And it's that if you have a nice atom with n+1 vanishing moments, and you apply the radial maximal function T applied to A, then far away from the support of the atom, this quantity decays, and I'll explain why this is decay. You just have the maximal operator applied to the characteristic function of Q raised to this power. And notice that the bigger n is, the larger this exponent is. Away from Q, this decays, like 1 over x to the n. So you're raising it to some very large power. So what the regularity gives you is far away from the support, this quantity decays very quickly. Okay. So the second thing we're going to need is a vector-valued inequality. In the unweighted case, vector-valued inequalities for the maximal function are due to Pfefferman-Stein. In the weighted case, almost as old due to Anderson and John. What I want to stress, though, is a vector-valued inequality like this is an immediate consequence of the scalar inequality using Rubio-Differentia extrapolation. Okay, so these results were already known, but in the future, if you ever need vector-valued inequalities, Rubio-Differentia extrapolation is the tool to prove them, because you can deduce them from corresponding scalar inequalities. Okay, so with this in hand, how do we argue? Well, first, notice this was the exponent from the pointwise inequality. And then the regularity condition we chose on big N, remember it involved R sub W. Okay, which AP class does W lie in? And this exponent is such that W lies in A tau times P. Okay? And then what do we get? Well, the global term, we use the pointwise estimate. We replace m phi t of A just by m applied to a characteristic function. We raise everything to the power tau divided by 1 over tau, and then we get this expression. So notice the weighted inequality goes from LP of W, P possibly very close to 0, to LP tau of W. And W is in that Muchenhaupt class. So by the Pfefferman-Stein inequality, the characteristic function, excuse me, the maximal function goes away. We just get the characteristic function. The power tau vanishes because the characteristic function is equal to 1. We can get rid of the power 1 over tau that we introduced, and we get this expression, the LP norm of linear combinations of characteristic functions. But remember, this is the Hardy space norm of F by the finite atomic decomposition. So the global piece is done in a page. The local piece is more complicated, but we need the following vector-valued inequality. In the unweighted case, this was proved by Grafakos and Kalton when Q is equal to 1. It's very, very difficult to prove, or at least their proof is very difficult, because notice that you have these functions gk, each of which is supported on a Q. We do not assume that the qk have disjoint support. And the sum, while it could be finite, it could also be infinite. So the supports could pile infinitely deep. Okay. We proved it in a very different way using a slightly modified form of extrapolation called reverse Holder extrapolation. So for those of you who want to know, what you do is you have to assume that the weight satisfies a certain reverse Holder inequality, and then you can extrapolate in the scale of reverse Holder weights. Okay? And again, you prove it in a simple base case, and then you extrapolate. And again, a much simpler argument to prove this using extrapolation. The key here is P will be, for us, will be fixed, but we can take any Q bigger than P. That's all the theorem requires, is that Q is bigger than 1 and is bigger than P. And so how are we going to use it? Well, W is an A infinity weight. So by the structure theory for these Mugenhaupt weights, it satisfies a reverse Holder condition, possibly with an exponent very, very close to 1. So what do? P is fixed. We fix Q so large that the dual exponent Q over P prime is very close to 1. So you get the reverse Holder inequality. And again, remember, we have this inequality here for any Q large. So then if we do that, we can apply the lemma, and the local term, we can replace the sum of M phi T AI by these averages. What does that get us? Okay, notice these are unweighted averages. Okay, so in particular, since Q is bigger than 1, M sub phi is bounded on LQ. T is bounded on LQ. So we can peel those off. The support of AI is still QI, so the integral remains the same. And now we have an LQ average of an atom, but it's an L infinity atom. So this whole term right here is bounded by 1. So it just goes away, and we're almost, excuse me, please, to what we want. But notice that the support is not QI, but QI star. So this is much bigger than what we need. But here's what you can do. For any tau, this characteristic function is up to a constant bounded by the maximal function applied to the characteristic function of the cube. That's because this cube is just a fixed dilation of the smaller cube. You can find a constant which makes this true. And this is exactly the term that we estimated in proving the global piece. So again, we repeat the argument from the global piece, and we get the Hardy space norm of F. And that finishes the proof. Okay. So this is probably the nicest proof I know. I claim it's the nicest proof of these weighted norm inequalities. And even in the classical case, this gives a very clean proof of the Pfefferman-Stein inequality. What's different, however, is you do have to invoke a lot of machinery in the background of Rubio-de Francia extrapolation to prove the vector-valued inequalities. Okay. Let me spend a couple minutes talking about some other results that we can prove in this way. So we can extend our bilinear results so that instead of mapping into LP of W or LP punto, we can map into the corresponding Hardy space. Okay. But to do that, we just need to add more regularity. Okay. It's a similar looking expression, a little more complicated. Roughly, you have to double the amount of regularity, so big N has to be approximately twice as large. We've also been able to do this for much more general operators. So instead of looking at singular integral operators, we can look at multilinear multipliers with very generalized Sobolev type regularity conditions on them. And I think there's some really interesting things to do there because we built some machinery for a family of very generalized operators, which include the multilinear multipliers. And I think those could afford to be explored better. And then lastly, the so-called multilinear fractional singular integral operators, which are sort of a singular version of bilinear Riesz potentials. They show up and people find them interesting, so we were able to extend our results to that setting as well. Some open questions. In the bilinear theorem, the regularity condition, remember, n depended on both spaces, but we had to assume the regularity on both pieces of the kernel. Okay, and it seems to us that you should be able to separate these out, and depending on which Hardy space you have for H1, HP1, and HP2, you should be able to have different regularity on the kernel in the first and second terms. We have some ideas sketched out for that, but we haven't been able to write them down yet. This whole theory, especially the linear theory, should extend to Hardy spaces defined over other function spaces. I think there's a good project lurking there. I keep hoping to get a graduate student who's good enough to do it. You should be able to do this for Hardy spaces defined over other function spaces. So Hardy-Orlich spaces, Hardy spaces defined over generalized Orlich spaces, those kinds of things. And then lastly, this whole theory ought to extend to other kinds of Hardy spaces. So in the past 10 or 15 years coming out of PDEs, there's been a lot of interest in Hardy spaces defined with respect to different kinds of kernels that come from various kinds of elliptic operators. That whole Hardy space theory is very complicated, but our ideas ought to be able to be used to simplify that theory as well. I think that's a very deep and interesting question. So with that, let me go ahead and finish and say spasibo, and thank you all very much. And since I'm from the University of Alabama, I must finish by saying roll tide, even though none of you know what that means. So thank you all.
David, thank you very much for very nice talk. And we come to questions. Maybe I'll have first question, just a general wondering. When you explain us very clearly this very nice splitting into global part and local part and very nice technique used. So is it specific of Hardy spaces or is it just general ideas that can be applied for different spaces?
I would think it could be used to analyze any of these bilinear kernels, or in the linear case, could probably be used in other spaces as well, because it's just making use of, in some sense, it's like the Calderon-Zygmunt good-bad decomposition. You localize to where the function is bad, which in the case of an atom is just its support, and where it's good, which is far away from this. So yes, I think this decomposition could be used in other settings. Okay, and one small question yet. When you speak about inverse Gaussian inequality, you just take the construction of inverse Gaussian inequality and extrapolate and have a condition for weights, right? Yes. Okay. So well, I will go back to the theorem so you can see what the idea is. So the theorem basically says that if you could prove the inequality in this lemma for a fixed P and a fixed Q, then you can extrapolate to all Q. Or vice versa, if you can prove it for a fixed Q, then you can extrapolate to all P. I think that's the way the theorem works out. Okay. Okay, perfect. Thank you very much. Okay, guys, questions, you can raise your hand here in Microsoft Teams. Please, questions. We have a lot of people here, more than 50 people.
May I ask a question?
Yes, of course. Go ahead.
Thank you, Alexey. Okay, so I'd like to see page 17. It's all right? Page 17.
This page?
Yes. So we can find the double here. So how regular is double? And which AP class does double belong to?
W lies in, that's a good question. Roughly, it lies in, if W1 lies in AQ1, well, here, let me abuse notation and simply say, suppose that W1 was in P1, AP1, and W2 was in P2, then W will be in AP, where P defined this way.
It must be greater than or equal to 1.
Excuse me?
Yeah, sorry. So P must be greater than or equal to 1 in that case.
Yes, that's, so if W1 will belong to some class, call it AQ1, W2 will belong to some class AQ2. Define Q to be the harmonic mean of Q1 and Q2, then W will be an AQ.
I see. Thank you. Understand. Thank you so much.
Mm-hmm.
Okay. So more questions, please.
May I ask you one more question?
Okay. Go ahead, please.
So could you please go to page 31? Yes. So you proposed second problem. Okay. So how to say? Suppose we want to consider bilinear theorem about Hardy spaces defined over other function spaces. Okay.
Mm-hmm.
Suppose we have a Hilda inequality. So script x and script y are some function spaces, and we have some information of the product of f in x and g in y, or something like this. X times y is contained in another function space g.
Yes.
Suppose I know something like this. In that case, so can we extend our result with ease to such a situation?
You would need two tools. You would need to be able to do a finite atomic decomposition in the Hardy space to find out x and the Hardy space to find out y. And you would need,
I see.
And then you would need the boundedness of the Hardy-Littlewood maximal operator on these spaces,
we need.
x and y, in order to make the extrapolation theory work. So you would need a version of bilinear extrapolation to work in this setting.
I see. So, for example, it's a little bit demanding if I use Mori spaces because we cannot use some finite decomposition result. Am I correct?
You could, you can possibly avoid the finite atomic decomposition, but it will require, there will be technical difficulties because you will have to use an infinite decomposition, which will require more regularity on the kernel, and then you'll have concerns about convergence.
I see. So I think the second question is interesting one because I can consider this problem with my students. Thank you so much.
You're welcome.
Okay, thank you. More questions, please. Well, maybe I'll have some one more maybe stupid question, but just general wondering. Well, when you consider bilinear inequalities, and as you said that one P1, for instance, can be lower than below 1, and this P2 can be greater than 1. I'm speaking about variable case. So, but you have a general condition for action of operator. But can we say something in some particular case when P1 and P2 depend on each other, like in very simple sense, like P1 of x plus P2 of x equals to 1? Or it's just stupid question maybe?
I don't know an answer.
Yeah.
I think it's a reasonable question to want to couple the spaces and have their exponents track each other in some way. I don't know if that would give you more information. It might allow you to play with the regularity of the kernel in some way. I think in all of our results are not optimal because, like I said, in the weighted case, it does not reduce to Pfefferman and Stein if you take both of the weights equal, or Grabakos and Colton if you take both of the weights equal to 1. So
Yes.
we're losing information about regularity somewhere in the proof.
Yes. I understand. Thank you. Thank you. Okay. So, are there any question? More questions, please? You can raise your hands.
I would like to take this opportunity to say hello to Stefan and Natasha Sanko.
Natasha and Stefan Samko, can we hear us? Can you hear us?
Yes, yes.
Yes. Yes. Yes, we're here. Yeah, we're here. Hello to David.
It's good to see you again, Stefan.
Okay. Okay, so are there any question? Well, if there are no more questions, then please, those who can turn on camera, please turn on your cameras in case you can do this, and we take picture together. Can you do this? Turn cameras. Turn on cameras. Oh, yes.
Mm-hmm.
So we'll take some pictures from our seminar. Well, it's very nice to see so many people, so many good friends, and very nice talk. Thank you, David, again for very nice explanation of very great theory of Hardy spaces. And I see that there are many questions that can be an application of your further application of your research. And thank you very much. And well, no questions more. Then thank David again.
Thank you again for this